Okay, I've gotten a few questions. I think this is an interesting topic about negative volume. Can we have it? What does it mean? And it comes from an extension of thinking about things in R2, where you can, in R2, be, say, getting the area under the curve, y is a function of x, from, say, A to B, so this area. And if you just compute this as an integral from A to B, f of x dx, know that you're getting a net area, right? Not necessarily a physical area. So it's actually going to subtract out this part here. You could like flip it around, maybe taking out like that much. And really we would just be getting this red when we do the definite integral. But if we wanted the physical area, this represents the amount of paint we need to get, or something in landscaping, amount of pavers, well, then you want the physical area. And so you'd want to do something like this. If this was the point C, to get the physical area, you would do integral from A to C, f of x dx, negate that, or take the absolute value, however you want to think about it, because this part is definitely negative because it's below the x-axis. Negate it makes it positive, plus from C to B, the part that is positive gets to stay that way, right? We have something very similar happens in R3 when we're talking about volumes. So we can have negative volume. And maybe let's look at this function just because it's easier to graph. Z equals sine x, we have a free variable, y is free. And so what happens then, oh, also, I just thought of this, I don't know why I didn't think of this earlier, but your journals, right, we talked about, oh, you can like write on the back, but you could actually, both pages are transparency. So maybe like slide a little, and I should probably do this on future covers, make that like a graph paper page under there. So you have 2 pages of graph paper, this can be your y-axis. There's my actual y. And then I can write them both, and I can stick my pen in here, right, to be the z-axis. And so if that's the case, if this is the xy plane, then what we have for z equals sine x, here's the z-axis. Sine x comes like this, and then below, and then it runs along the y-axis, which is along the coil, so it would run this way. So hopefully you see that here. You could take a piece of paper and bend it and get that shape. But we can also just, should be pretty good at doing this by this point. I'm going to put the x, y kind of skewed in here, put the z vertical, and then sine x, oh, let's make a region too. Let's say r is, let's say negative pi halves to pi, cross, that's the x. That's another way of saying negative pi halves less than or equal to x less than or equal to pi. Cross, let's just say 0 to 1, keep the arithmetic easy on the y. So we'll come like this. There's pi. And then negative pi halves would come to like there. But then this runs, that's just in the zx plane, and then it runs along the y from 0 to 1. So this will be 1 along the y back here. So again, in the xy, 0 to 1, pi halves is, say, like, there pi is here. Let's see, this is negative pi halves. So we have this rectangle is R. And this now extends over that rectangle. So because y was free, I'm going to make another copy in the y-axis. It runs along the y-axis. So I'll copy that there, connect the ends. Right here, come under. And so it's a curved function, a sine function that runs like the y-axis. Some of it is above the xy plane, some of it is below. And so if we were doing an approximate volume, we could decide how many rectangles we want to divide this into, decide what the x partitions are, how many y partitions, and get an approximate volume. And we can also, depending on where you are in the journals or video lectures, you might know that you can also do this exactly with integrals. And so the exact volume would be double integral over this function It doesn't matter whether we do dy dx or dx dy because the constants are both, in both cases, are all, the limits of integration are always constant, so you can switch them. Or so you could have written dx dy. And this will give us our exact volume. But because some of it is below the xy plane, that is a net volume. There's part of it that's going to be negative. And so if I actually wanted a physical volume, I'd want to make sure I divide this. And I now know when x goes from negative pi halves to 0, I actually get the part that's below the xy plane. So that'll be a negative volume. Why will that be negative? So when we put the integral, and then let's talk about why that's going to be negative. So when x goes from negative pi halves to 0, y still goes from 0 to 1. We want to negate that because, again, this part lives below the xy plane. And again, the reason it would be negative is think about your approximate volumes. When you were maybe deciding to split this into like n equals 6 rectangles, maybe we'd do like that. So thirds along the axis, so pi halves, and then a half divided into y's. So making a total of 6 rectangles, or in your b minus a over m, d minus c over n, if you're looking at it that way. The dx's would be pi halves, the dy's would be a half, but the area of each rectangle is 1/2 times pi halves. But you have to get, after you take those areas, you have to get heights. And the heights on the ones here, whether, let's say we did the midpoint rule, when we get f for this guy, which is, let's see, 3/4, right? 3/4, oh, that's my height. My x is negative pi fourths, my y is 3/4. When we plug that into our function, we're going to get a negative because it lives below the xy plane. We'll get a negative for this midpoint, height-wise. And then these two will give us positive heights times positive areas, positive volumes. So we know that this part here, always above the xy plane, if we did it as approximate volume, is positive. If we did it as exact, is positive. So we can add that second part, which goes from 0 along the x to pi along the x, and then 0 to 1 on the y still, sine x dy dx. This part always lives above the xy plane, and for that reason, the heights, these signs, always evaluate to positive numbers. On the other hand, these signs between negative pi halves and 0 evaluate to negative, we'll negate them. That'll give us our physical area. So let's just check some of that we see in our super expanded desktop coordinate system, or we see it drawn in R2. Well, let's look at it in a tech tool with CalcPlot 3D. So share the screen. Let's go to CalcPlot 3D. I usually always have something up on that. Okay. So let's see if we've got our region here. Our region, we want to say y is from 0 to 1, and then x goes from negative pi halves to pi. And the surface is sine x, so I put the 3D, and we want to go from the surface, that's this nice little curved surface right there, or maybe a better way to display it is right here, sine of x. Okay, so there we go. That is negative pi halves to pi along the x, 0 to 1 along the y. Let's just look at that. Whoops, that first. Okay, chill. All right, better use my arrow keys. Take a look again as maybe I'll zoom in. Not a very pretty color they chose, but again, you can change the color of the surface. Here's the part above the XY plane, and maybe to orient it a little bit more like the picture I just tried to draw on the board, maybe it's kind of something like that. Here's the part below the XY plane, So if I'm going to get a double integral, which gives me exact volume, or I'm going to do an approximate integral with double Riemann sums, I'm going from this surface always to the xy plane. And so this little region here will give me negatives. Well, let's see what happens when we do that with defining a region. That was the one we'd already put in. Let me take that surface off. Okay. So we had already put in, we added a region to the graph, select region, and we got to here. We entered the region and checked up here in this yellow that that is what we want. Let's see, they're doing it with more rectangles. So let's go ahead and like put in the one I was just doing an example. We did 3 in the x direction and 2 in the y direction. And I was just showing the midpoint rule, so we'll keep that. And again, notice that these blocks are above the xy plane, so when we get volumes, those will be positive. These ones will be negative. Let's see what happens. We can show the height, the points that are used. And the volume of this is about 1.11. Okay, well, how does that compare? So let's actually just take the part that's right here from x goes from 0 to pi and see if we should get a value that's more than the 1.1, right? Because it's living above that. So let's check it. Yeah, so there we go. The volume is 2. So what happened is from the 2.09, you subtracted out how much? Let's get that exactly. You subtracted out the negative part. That went from negative pi halves to 0. That part right there is a negative 1.1. So you took the 2.09, subtracted out this negative 1.1011, and you got a net volume. But again, if you wanted a physical volume, you would take this negative 1.01, negate it, make it positive, so it'd be positive 1.01, and then add to that what happened on from 0 to pi, which was that part over here, which was like 2. So we're gonna have something around 1 plus 2 is about 3 when we get our physical volume. I think I said area before. Physical volume. And same thing would be the case if you were doing it exactly with double integrals. Okay, hope that clears up something about, those are really good questions. And this time in the semester, it's really neat to see, I start seeing students asking extension questions or generalization questions or connection questions. So that was a great one. Thanks for asking that, and I hope that clears it up.